Welcome to the video lecture on work. Work is the measure of energy needed to perform certain jobs, like a truck pulling a load, a crane lifting an object, compressing or stretching a spring, propelling a rocket, etc. And when you talk about work, you need a force. A force is a push or a pull. It changes the state of rest or state of motion of a body. Now, if you have a constant force acting on an object, then the work that is created is force times distance. So this F here is our force, which we're going to assume is constant, times our distance. So for example, if you want to figure out the amount of work required to move a 100-pound object a distance of 3 feet, then the work would be the force, which is in this case the weight of that object, which is the 100 pounds, times the distance that we want to move it, which is our 3 feet. And so this would be 300, and notice the units here. We're going to call these foot-pounds. So in our different metric and U.S. systems of measurement, work in the U.S. system is measured typically in foot-pounds, inch-pounds, or foot-tons. In the metric or CGS system, the measure of force is usually measured with a dyne, which is the force required to produce an acceleration of 1 centimeter per second squared on a mass of 1 gram. So we would measure work using dyne centimeters or dyne ergs and Newton meters or Newton joules, where 1 joule is 10 to the 7th ergs. Now let's talk about what happens if you have a variable force, not a constant force. If the amount of force changes as the object changes position, this is called a variable force, and that's when we're going to need calculus. So you can think about the amount of work or the change in work as the force at a certain moment in time times the change in distance. And as we add up all these little distances, this change becomes an integral, and the work becomes the integral from A to B of our force function times dx. So one very typical example of work problems are these spring problems based on something called Hooke's law. So the force F required to stretch or compress a spring within its elastic limits is proportional to the distance x that the spring is stretched or compressed from its natural length. And remember that if something is proportional to, that means it's a constant times. So we're basically saying here in Hooke's law that the force required to stretch or compress a string is k times the distance that it's stretched or compressed. So F equals k times x. So usually in these spring problems, they're not going to directly tell you this constant of proportionality, this k, but they will give you enough information to figure it out. So you'll need to find that k first, and then once you know what that k is, you can write out your force function, and then you'll be able to integrate that force function using the idea that work is the integral of force times dx. Okay, so for example, suppose that a force of 5 pounds compresses a 15-inch spring a total of 4 inches. So right away, this is going to tell us what our constant of proportionality is for this particular spring. We know by Hooke's law that force is k times x. So how much force do we need to compress this spring? We need 5 pounds of force, so 5 is my F. And what am I compressing it? I'm compressing it a total of 4 inches. You don't actually use this 15-inch at all, at least initially in this part of the problem. You just want to know how much you're actually compressing or stretching it, which is this total of 4 inches. So we're going to use 4 for our x, which means that when I solve for k, k is going to be 5/4 or 1.25. So that makes this force function become 1.25 times x. For this particular spring, this is the force function on it. So to calculate the amount of work it takes to stretch or compress it, we're going to need to integrate this force function times dx. Now we need some bounds on here, so let's continue to read here. It says how much work is done in compressing this spring from a length of 10 inches to a length of 6 inches. So this is where that initial or natural length of the spring comes into play. Initially, this spring is a 15-inch spring. So it's going to look something like this. And what we're doing is we're compressing it from 10 inches down to 6. So the tricky part about these is the bounds, because what you want to use for your bounds is how much from the natural length is the spring being compressed. So if initially we're at 15, to get it down to 10 requires a distance of 5 inches, and to go from 15 down to 6 requires a compression of 9 inches. So the bounds that we want to use are that 5 and that 9. So my bounds on this work integral are going to be from 5 to 9. So then this is actually a pretty easy integral to solve. We can pull out that 1.25, and the integral of x is x squared over 2. And we're just going to plug in our 5 and our 9. So this will be 1.25 times 81 over 2 minus 25 over 2, and you can punch that into your calculator and it comes out to 35. Now in terms of the units, remember that our force was in pounds and our distance was in inches, so this is going to be inch pounds for our work. Okay, so let's try another example. How much work is done to stretch a 15-inch spring from a length of 20 inches to a length of 24 inches if a force of 5 pounds stretches the spring 4 inches? So again, you would initially start with your force function, and for every spring that's going to be F equals K times X. And this spring is actually the same as the one in the previous example, because it tells me that it takes 5 pounds to stretch this spring 4 inches. So my X is 4 when my F is 5, and that makes this K 5/4 again, or 1.25. So my force function for this spring is F equals 1.25 times X. So your work integral is going to be the integral of this force function, 1.25x dx. And now we just need to figure out what our bounds should be. So again, we're starting with a 15-inch spring, but this time we're going to stretch it out from 20 out to 24. So you always want to measure from the natural length of the spring, which was this 15. So initially, when I go out to this 20, that's 5-inch stretch, and then to go out to 24, that would be a total of 9-inch stretch. So my bounds again are going to be from 5 to 9. So it's exactly the same problem and integral as the last one, even though we're stretching this time instead of compressing. So this work integral is going to give me the same answer as before, 35 inch-pounds. Okay, so for these spring problems, you're going to be using Hooke's law, F equals K times X. Find your constant of proportionality K first, and then you're going to be integrating that function, that force function, using appropriate bounds based on how much you're stretching or compressing from that natural length. So now we're going to move into a different kind of a work problem. These tend to be a little bit tougher to do. These are going to be work problems on moving fluids, how much work it takes to move some fluid. So in these problems, our amount of work, our change in work, is going to be our force increment times our distance, or our change in our force times the distance that we need to move it. And in these problems, typically what we're going to think of is the force as being the weight of a slice of a cross-section. So we're going to have some shape, we're going to take a cross-sectional slice, and we're going to calculate the weight of that slice. And in these fluid problems, typically you're going to find that weight by using the fact that weight is density times volume. And they will usually tell you in the problem what the density is for the particular fluid that you're using, and then you'll be able to calculate the volume based on the shape of that cross-section. So to begin with here, we're going to start with a fish tank with a rectangular base having width 2 feet, length 4 feet, and a height 3 feet, and this tank is full of water. Find the work done to pump the water over the top edge to empty the tank. And we're going to be told here that the density of water is 62.4 pounds per cubic foot. So this is our fish tank right here. Okay, I'm going to show you how to do this in two different ways, and it'll be your choice how you choose to do it. In some of the later problems, it can be slightly easier to do it one way or the other depending on the problem. So for this first problem, what we're going to do is we're going to take a cross-sectional slice out of this fish tank, and that's what this red little slice is right here. And we're going to let the thickness of this slice be delta y. So that's its thickness, and we're going to calculate the volume of this slice, and since it's in the shape of sort of a very thin rectangular box, its volume is just its length times its width times its height. So we're going to use that volume formula to come up with this weight. Now to begin with, remember that weight of our slice is going to be the density times the volume. Weight is not just volume, it's density times volume. So this weight is going to be the density of our water, which they tell me is 62.4 pounds per cubic foot, and we're going to multiply that by the volume of this slice. And as I said before, this is basically just a rectangular solid, so its volume is going to be its length, which is 2, times its width, which is 4, times its height, which is this delta y. So when we do that, this becomes 62.4 times 8 delta y. And this is a foot, this is a foot, and this is a foot, so the foot cancels out the cubic feet on the bottom, so this is going to actually give us pounds. And now we've turned this volume, using the density, into a weight, and in this context, this weight is actually going to be the force function that we're going to be using when we do our work integral. Remember that work is always the integral of your force over a distance. So now we have our force right here. Okay, so what we need next is our distance. We have our force, now we need our distance. So we're going to calculate the distance that the slice must move to the top of our tank. And that's because we want to pump this water over the top of the edge of the tank to empty it out. So we want to have it overflowing over the top. Now this is where these two problems are going to differ, how you decide where to measure your distance from. So one option here is to measure your distance from the bottom of the tank. So I would call this vertical distance here y, and we're going to let y go from the bottom all the way up to the top, and it's like we're moving that slice of water slowly up over the edge of the tank to empty it out. So if this being measured from the bottom is our y, then the distance that this red slice needs to actually move to get to the top is this distance right here, up above. We need to move this red slice, that green amount, up to get it over to the top. So if I'm measuring y from the bottom, and this entire height of the tank is 3, then how much is this green distance here? Well, it would be 3 minus however much my y is. These two things need to add up to 3. So the distance that this red slice needs to move would be 3 minus y. Okay? So now that we know our force and our distance, then we can write down our work, because our work is going to just be the integral of this force right here times our distance here. Now this delta y becomes a dy when we integrate. This is kind of like our change in work when we multiply by that delta y, and if we make that delta y get smaller and smaller and skinnier, then that turns it into a limit, which turns it into our integral. So our work integral will be this 62.4 times this 8. This delta y is going to become a dy, and my distance, I'm going to use parentheses here, will be that 3 minus y. So here's my force, and here's my distance. Now all I need are my bounds. So we look at this y and we figure out how y needs to change. Well, the bottommost slice on the bottom would be a height of 0, and I need to go all the way up to the top, which is at a height of 3. So my bounds are going to be 0 to 3. So this is my work integral. Now to actually calculate this, if you want, you can pull that density out. You could even pull the 8 out if you want. So all we're really integrating is that 3 minus y, and that comes to 3y minus y squared over 2. And when I plug in my bounds, 3 times 3 is 9, 9 squared over 2, or 3 squared over 2 is 9 halves, and when I plug in 0, both of those go to 0. So this is going to give me 62.4 times an 8 times 9 minus 9 halves, and that's just going to give me, as a decimal, 2246.4. The units on this, since we were using measurements of feet for our distance and pounds for our density, this is going to be a foot-pound. So it takes me 2,246.4 foot-pounds of work to empty out this fish tank. Okay? Now, just to show you an alternative here, we're going to do this same problem again, but I'm going to make one slight change. Now, the weight of my slice is not going to change at all. In these two problems, I'm going to do that exactly the same. So this thickness would be my delta y. To get my weight, I need my density times my volume. So the density of water is 62.4, and the volume of this cross-sectional slice is its width, which is 2, times its length, which is 4, times its thickness, which is that delta y. So this is going to still be that 62.4 times 8 times delta y. And that delta y turns into our dy once we turn this into an integral. Okay? So then the only change between this problem and the last one is my distance function. And it's just based on how you define your y, where you place that y. So up here, I measured y from the bottom of the tank up. Down here, what I'm going to show you is the alternative of measuring y from the top down. So I'm going to let this height coming down from the top of the tank down to my slice be y. And what that does for me is it makes this distance function simpler, because now how much does my slice need to move to get it up to the top of the tank? It just needs to move up y. So my distance that I need to move that slice is just y. So my work integral becomes all of this weight, so 62.4 times 8, the delta y turns into a dy, times my distance, which is now just this y function. And my bounds are going to be 0 to 3, just as before, because if y is from the top down, I still need to go from 0 all the way down to 3. So same exact bounds for this particular problem. And so when I integrate this, we can pull out the 62.4 and the 8, so we're just integrating y, which is going to turn into a y squared over 2. And when you plug in your bounds of 0 and 3, you just get 9 over 2, and that is the same exact answer that we got before, 2,246.4 foot-pounds of work. So you might say, well, why don't we just do it from the top every time because it gives me a simpler distance function? Well, in this particular example it did, but in some problems that might not be the case. So sometimes it is easier to measure from the bottom up as opposed to measuring from the top down. Okay, so you want to be familiar with both options. Let's try another example, and again I'm going to show you both ways of doing this. So on this one we have a right circular conical tank with the vertex pointing down. It has a radius of 5 feet and a height of 20 feet. If the tank is full of water, find the work done to pump the water out over the top of the tank. So it's very similar to the last example. The only difference is our shape of our tank. Now we are dealing with a cone instead of with a rectangular solid. So just like in the last example, what we're going to start off by doing is taking a cross-sectional slice, which is this red little disc shape right here. It's going to have a thickness of delta y. And we need to calculate the weight of that slice because that weight is going to be the force that we need to move. So to get the work, we're going to take the force, which is the weight of this slice, times the distance that we need to move it, because work is force times distance. So let's start by calculating the weight of our slice, and that is going to be the density times the volume. And we're still dealing with water, so my density is still 62.4 pounds per cubic foot. And this time my volume function is a little bit different because what kind of shape does this cross-sectional slice have? Now it's no longer a rectangular solid. It's actually like a little disc shape. So to get its volume, we need to know the area of that top circle, which would just be pi r squared, where the r is that radius right there, times its thickness. So this is going to be pi r squared times delta y. Now keep in mind, because we're using delta y, and I chose delta y because this thickness is kind of in the vertical direction along that y-axis, that means that this delta y is going to turn into a dy integral. So this radius that I have right here needs to be something in terms of y. So what's y? Well, that's what we have to decide, where we're going to take our y from. So in this first example here, I'm going to measure y from the bottom up. So I'm going to let my y be that vertical distance right there. Now if I do that, that means I can figure out a relationship between this radius r and this height y using similar triangles. Because what we have here is the big radius 5 and the big height 20, and then nested within that is our smaller triangle, which has a radius r and a height y. And using similar triangles, I can set up a proportion. So 5 to 20 has to be in the same proportion as r to y. So if I simplify this, 5/20 is 1/4. And if I multiply my y to the other side, that tells me that 1/4 y is equal to this radius. So instead of using r over here, I'm going to replace it with 1/4 y. That way I'm only using one variable and it's consistently a y throughout the problem. So now my weight becomes my force. So this is going to be the force that we're going to be using when we do our work integral. What we need next is our distance. So the distance that I need to move this slice up and out over the top of this cone. So if this red slice is in this position right here, how far do I need to move it to get it up to the top? Well, if I have y height from the bottom, then what would be this height right here that's left for that red slice to go up to the top? The whole height is 20, and this bottom height is y, so that means this green height is 20 minus y. So I need to move this red slice a distance of 20 minus y to get it up to the top. So my work integral is going to be my force times my distance. So this is going to become my force function, which is all of this. So 62.4 times pi times 1/4 y squared. The delta y becomes my dy, and the distance that this slice moves is this 20 minus y, and I'm going to use that in parentheses. And how does this y vary? Well, at the very bottom, the height y would be 0, and if I take y all the way up to the top, then that would be a height of 20. So my bounds should be from 0 to 20. So here's my work integral. To solve it out, you could pull out the 62.4 and the pi, and the 1/4 squared becomes a 16, so you can pull that out. And what you're left with inside is just going to be that y squared times 20 minus y. Then you would need to distribute your y squared across, and then you're ready to integrate. So 62.4 pi over 16, and the integral becomes 20 y cubed over 3 minus y to the 4th over 4, and we're ready to plug in our bounds. I'm going to get 20 times 20 cubed, which is 20 to the 4th over 3, minus 20 to the 4th over 4, and when I plug in 0, that's just going to give me zeros. So if you punch all of this into your calculator, getting a decimal is fine. This is going to be 163,362.82, and the units again are foot pounds. So this is 163,362.82 foot pounds. Okay? All right, so let's do this same problem really quickly, just with one slight variation. So if I have my slice again here with my delta y being its thickness, then what I can do is calculate the weight of this slice by taking its density times its volume. Now the change that I'm going to make here is, instead of measuring the height of this slice from the bottom up, I'm going to measure my y from the top down. So this time I'm going to let this be my y. So what that does is it changes this volume slightly, because my density is still that 62.4, and if I let the radius of this slice be that r again, my volume is going to be the area of that circle, which is pi r squared, times its thickness, which is that delta y. And just like in the last problem, we want to figure out what this r is in terms of y, so that we're only using y variables. But by the way that I've positioned my y, that's going to change what this r function becomes, because I have a slightly different picture going on. Here's my new picture. I still have 5 and 20 here, and I still have my radius r here, but this time this distance here is y, which means how much is this distance here? Well, the whole thing is 20, and this top part is y, so that means this bottom part is 20 minus y. So my proportion is going to be a little bit different. I'm going to have 5 to 20, so the big radius to the big height, equals the small radius, which is r, to the small height, which is now this 20 minus r. So when I cross multiply, well actually 5/20, let's reduce that to 1/4. When I cross multiply, 1 times 20 minus y is 20 minus y, and 4 times r is 4r, and to solve this for r, I can divide by 4. Whoops. So my radius becomes 1/4 20 minus y, and you can distribute that across if you like. But that means this volume function is going to be a little bit more complicated than it was in the last example. My radius is now 1/4 times 20 minus y quantity squared delta y, and that's going to be the force that I use in my work integral. Now the radius got more complicated by choosing the y to be this upper part, but the consolation prize here is that the distance that this red slice moves becomes simpler, because this red slice, to move up to the top, just has to travel through that distance of y. So my distance function got simpler even though my radius got more complicated. So the work integral is going to be all of this, so 62.4 pi times 1/4 20 minus y quantity squared. The delta y becomes my dy, and my distance is just a y. My bounds for y, same as before. The height y has to start from 0 and go all the way down to 20. So my bounds are still 0 to 20. Now I won't go through all of the work, but this integral will give you exactly the same solution as the last one. It's just using that y from a different perspective. Okay, so you have your choice. And as you can see from this example, making a different choice for y can complicate one aspect of the problem but simplify another. So you have to kind of weigh which option is better for you. Okay, next example. Using the same tank from the last example, find the amount of work done to fill the tank if the water source is at the base of the tank. So this time the water is being filled in from the bottom down here and slowly is going to rise up and fill up this tank. Okay, so just as before, what you always want to do first for these fluid work problems is take a cross-sectional slice. Its thickness is going to be this delta y, and we want to figure out what the weight of that slice is going to be. And that's going to be its density times its volume. We're still talking water here, so density is 62.4 pounds per cubic foot, and this volume function, again, since we're dealing with a disk, is going to be pi r squared, which is the area of that circle, times its thickness, delta y. So here's where we need to make our choice, and I'm not going to do it both ways this time. We're just going to decide which way we want to go with. Let's decide to change or to pick our y to be from the bottom up. So I'm going to let my y be this distance right here. So you need to make that choice for yourself, whether it's from the bottom up or from the top down. Now, based on that choice, that can help me determine what this radius function needs to be in terms of y. So if I go to my similar triangles again, this is 5, this is 20, this is r, and this is y. So 5 to 20 equals r to y. This reduces to 1/4. So 1/4 y is what the radius is. So this becomes 62.4 pi times 1/4 y quantity squared delta y. And there's my weight, or my force. Now that I know my force, I need my distance, because work is force times distance. So how far does this slice need to move? Now remember, we're filling this up from the bottom up. So slowly as I fill this up, that slice needs to go up from the bottom up to the top. So how much is this slice of water moving? It's going to start at the bottom and it's going to go up to where this slice is. How much distance has that traveled? It's traveled that blue height y. We're no longer pumping it out over the edge. We're going from the bottom up, which is exactly how I define my y. So the distance that this red slab moves, since it's starting from the bottom and filling up, is just y. So my work integral is going to be all of this force, 62.4 pi times 1/4 y quantity squared, the delta y becomes my dy, times my distance, force times distance. And then the bounds for y, we want to fill this whole tank up. So from the bottom, that height y would be 0, and to fill it all the way up, it needs to go up to a height of 20. So my bounds would be from 0 to 20. So I'm going to pull out my 62.4 pi. 1/4 squared becomes a 16, which I'm going to pull out in the bottom. And what I'm going to be left with is this y squared times y, which is y cubed, And when I integrate that, that's just y to the 4th over 4 from 0 to 20. Plugging in 20 gives me 20 to the 4th over 4. Plugging in 0 will just give me 0. And when you punch that into your calculator, you get 490,088.45. So 490,088.45 foot-pounds of work. Okay? All right, next example. Using that same tank again, find the work done to fill the tank if the source of this water is 15 feet below the tank. So suppose this is coming from a water source that's 15 feet below the ground. Okay, and we still want to fill this tank up. So I am going to, since I'm filling the tank up, I'm going to choose my Y to be from the bottom up, just like in the last example. I'm going to let the thickness of my slice be delta Y. So the weight of my slice is going to be the density times the volume, which is going to be 62.4 times, if this has a radius r, this volume is pi r squared times delta y. Area times height. And this radius function, just like before, is going to be the same since we're dealing with the same similar triangles, 5 to 20, r to y, so 5 over 20 has to equal r over y, so 1/4 y equals to r. So far nothing has changed from the last example. Okay, so all of that weight is the same. Now here's the change, the distance. The water starts down here. So how far does it need to travel to get up to this slice up here? It needs to travel that initial 15 feet to get to the bottom of our cone, and then it has to travel an additional y to get up to this current slice height right here. So the total distance that's traveled by this slice was the initial 15 plus this y. So the distance traveled is 15 plus y. So my work integral is going to be all of this times this distance, use parentheses. And I want to fill the entire tank again. So how does y need to change? Y being 0 would be the bottom of the tank, and it needs to go all the way up to the top of the tank. So my bounds are still going to be 0 to 20. It's just how much the y changes. The y is not affected by the 15. It's just how the variable y is moving up and down. So this is going to become 62.4 pi over 16 from 0 to 20, and I'm going to get a y squared times that 15 plus y. So that's going to give me 15y squared plus y cubed. So when I integrate that, I'm going to have 15y cubed over 3, or just 5y cubed, plus y to the 4th over 4 from 0 to 20. And you can plug in the 20, the 0 will give you 0. So this is going to be 5 times 20 cubed plus 20 to the 4th over 4. And as a decimal, that is going to equal 980,176.91 foot-pounds. So over 980,000 foot-pounds of work. Okay? Okay, in this next example, we have the top of a cylindrical storage tank for gasoline at a service station is 4 feet below ground level, so it's buried underground. The axis of the tank is horizontal, and its diameter and length are 10 feet and 12 feet respectively. So you've got 10 feet across here and 12 feet long. It's lying on its side, buried 4 feet below ground. Find the work done in pumping the entire contents of the full tank to a height 3 feet above ground level. So not only do we have to pump the gasoline up to ground level through 4 feet, but an additional 3 feet to get it up through that gas tank. Okay, So in this problem, since we're dealing with gas, we're going to have a different density. The density of gas is a little bit less than water. It's 42 pounds per cubic foot. And for these problems that we're going to talk about where you have a circular sort of shape as part of your cross section, these are a little bit trickier to do, and the trick is to not measure the y from the bottom up, which we've been doing in some of the previous problems, but instead we're going to center our circle at the origin and either measure y from the top of the circle down or from the center of the circle up. So here's my diagram of that tank, and what we want to visualize again is that slice, that cross-sectional slice. You can see that it has sort of this shape in red here. It looks like a great big rectangle with a thickness or a width of delta y. Along the greatest part of the circle, the diameter, this would be 10 going across here and 12 going along here. So your volume would be this length times this width times this height. But as the slice moves up to a higher portion of the circle or a lower portion of the circle, that width is not going to be a full 10. You can see from up here along our circle that width is going to be smaller than our diameter of 10. So what we're going to do is we're going to call that width W, and I'm actually going to let W be the radius of that width. So I'm going to let W be this distance right here. So that would be this radius. So the entire width going across requires 2 of these W's. So to get the weight of our slice, we're going to take the density times the volume. And again, we're dealing with gasoline, so our density is now 42 pounds per cubic foot. And for our volume is going to be the volume of this slice, which is 2W going across, and that's going to vary whether we move up the circle or down the circle, times the length here, which is 12, times the thickness, delta y. So it's going to have a volume of 2W times 12 times that delta y. So our whole weight of our slice, 42 times 2 times 12, is 1008 W times that delta y. Now this W is not a y variable, and we are going to have a dy integral because of this thickness being delta y. So we need to figure out what W is in terms of y. And that's where this circle comes in, and that's where these hints that I give you here come into play. So here's what I recommend on a problem like this. Take this circular face and imagine centering it at the origin on a set of axes. So here's my circle. It's a circle of diameter 10, so the radius here is 5. This would be minus 5, this would be minus 5, and this would be plus 5. And any radius from the center out is also going to be 5 as well. Now our W is this width, this radius of that width going across. So just draw in a generic sort of cross-sectional slice, and that's our W. And what we want to figure out is the relationship between W and Y. So here's your two options. Option number 1 is to measure your distance y from the top of the circle down. So I have that in blue right here. So this y would be this vertical distance up here. Now based on that, what we're going to need to get is a relationship between W and this y. So how can we figure that out? Well, we can realize that this little W right here, along with this diagonal radius that I drew in, forms a right triangle. If this is y and the entire radius from the top here down to the center is 5, then that means this height or this leg of my right triangle must be 5 minus y. So what we have is a little right triangle where the two legs are W and 5 minus y, and the hypotenuse is 5. And we can use Pythagorean theorem to get an equation for this relationship. So W squared plus 5 minus W quantity squared equals to 25. And if we solve this for W, we're going to get W squared equals 25 minus this quantity squared, You can go ahead and expand that out if you want. I'm just going to leave it like this for now. And then I'm going to take the square root of both sides. And I'm just going to use the positive square root since we're talking about distances here. So this is what W equals in terms of Y, and that's what I need to put up here for this W. So my weight, which is also going to be my force, becomes 1008 times the square root of 25 minus 5 minus W quantity squared delta Y. So now we know our weight. What we need to know next is the distance that this slice needs to make. So first of all, if this is my slice, how far does that slice need to move to get to the top of the circle? Well, it needs to go from the top here up to that circle, which is exactly what we're calling Y. This distance right here is our Y. So my slice needs to move up Y to get to the top of the circle, and then don't forget, we still need to travel 4 more feet to get to ground level, and then an additional 3 feet to get to the height of the pump. So my total distance is this initial Y to get me to the top of my tank, plus an additional 7 feet to get me to the gas pump. So there's my distance function. So now my work integral is going to become the integral of all of this weight right here. So 1008 times the square root of 25 minus 5 minus y quantity squared. The delta y becomes my dy. And then this distance is just y plus 7. And then the bounds for this. How does y need to vary? Well, y is going from the top down. So at the very top, y would be 0. And what distance would it be for the y to measure all the way down to the bottom of the circle? Well, that's that diameter of 10. So my y would need to go from 0 at the very top of the circle, if that's where it started, to all the way to the bottom of the tank, which would be a total distance of 10. Now this is a not so nice integral to solve. You probably could solve it by hand doing some u substitutions and so forth, but this would be one that I would recommend just using that function integrate command on your calculator, since it's not too pleasant to deal with. So if you do function integrate, you get 475,008.81 foot-pounds of work. Okay? So now the alternative here is, instead of measuring your y from the top of the circle down, we could instead measure your y from the center of the circle up. So y would be this distance right here. Now my w is still going to be that width going across. So my weight of my slice is still going to be that density, which is 42, times the volume, which was this whole width going across, so that's a w plus another w, which is 2w, times our length, which was 12, times our thickness, which was this delta y. So this is going to be that 1008 w delta y. So that hasn't changed. But because of the way we're now redefining our y from the center of the circle up, it actually makes this triangle a little bit simpler, which is one of the reasons why people sometimes do the problem this way, by measuring this y from the center of the circle up. Because now we have a right triangle that looks like this. So w squared plus y squared equals to 25. So w squared equals 25 minus y squared. So w is just the square root of 25 minus y squared. And so now my weight function is a little bit simpler than the other one we had, where instead of a y squared here, we had that 5 minus y quantity squared up here. So it's a little bit cleaner. Now if we define our weight and our y this way, then how much distance does this slice need to move? Now this is going to be a little bit different now, because if my y is going from the center up, how far does this red slice need to move from where it is right now to get up to the top of this gas tank? Well, if this is y, it needs to move this distance right here to go from where it is right now up to the top. So what is that distance? Well, if this entire radius is 5, then this would be 5 minus y. So the red slice needs to go a distance of 5 minus y units just to get up to the top of the tank, plus that additional 7 units to go to ground level, plus up to the top of the gas pump. So this gives me a new distance function, which is actually going to be 12 minus y. So by reorienting where we position that y from, you get a simpler square root, but you get a slightly different distance function as well. So my work integral here would be all of this, so 1008 square root of 25 minus y squared dy times this distance wrapped in parentheses. And the other change that we're going to have is our bounds, because now y is starting at the origin here. It's being measured from the center of the circle up. So if we consider 0 to be the center, then y needs to go up to 5, but it also needs to go down to minus 5 to sweep through this entire tank. So the bounds here are going to be negative 5 to 5. So that's also going to be different from how we did it in the last problem. So both of these options are valid. You can do it whichever way you like, and no matter which way you do it, you're going to get the same solution, that 475,000 foot-pounds of work. Okay? All right. Moving on to our last type of work problem. So we've talked about work on springs. We've talked about the work required to move a fluid up or down. Now we're going to talk about the work required to move chains or cables. So in this kind of a problem, what you're going to be dealing with is a chain that typically you're either winding up or moving up or down. And what we're going to assume here is that our amount of work, our work increment, is going to be the force times the distance increment. So the force is times our delta x or our delta y. Now, I prefer to think of these problems in a slightly different way than the textbook shows you, but I'm going to show you both options, and you can choose whichever way makes more sense to you. So starting with this first problem, we want to find the work done to wind a chain 100 feet long, weighing 10 pounds. Okay, so we have a 100-foot long chain, and it's weighing 10 pounds, and we want to wind it up. So to visualize this, imagine that you have this pulley here, and you've got X amount of chain already wound up on this pulley, and then you still have some other chain length here hanging down. Now the more chain that hangs down, the more weight that it's going to have, which means the more force it's going to have pulling down. So you're going to require more work to pull it up if there's more weight hanging down. So the more chain that is wound, the less chain or weight that's pulling down, so less work would be needed. That means this is a variable force going on, and that means we're going to need an integral. So what we're going to do is we're first going to assume that X length of chain has already been wound around this pulley. So if X amount of chain is already wound up, how much is left hanging down? Well, there was a total of 100 feet of chain. So if X is already wound up, that means I have 100 minus X still hanging down. So there's 100 minus X feet of chain still hanging down, and that's the weight of that chain that we want to kind of associate with our force. Okay? So what would be the weight of this chain that's hanging down? Well, it's going to be using this relationship that 100 feet of chain weighs 10 pounds. I'm going to create sort of a ratio here. For this particular chain, it weighs 10 pounds per 100 feet of length. And if we reduce this, this becomes 1/10 of a pound per foot. So in the previous problems, we used density times volume. Well, here we're not going to do density times volume, but we're going to sort of think of this as sort of a linear density, if you will. It's the linear density of the chain. So to figure out the weight of the chain, we're going to take this ratio right here, 1/10 of a pound per foot, times the number of feet that we have hanging down, which we said was this 100 minus x. And the feet will cancel, which means we're going to get 1/10 of this quantity 100 minus x, and that will be the amount of pounds or weight of that chain that's hanging down. Okay, so that's your weight or your force, 1/10 of 100 minus x. What we need to figure out now is going to be our distance, and our distance is going to just be the dx that we see in our work integral. So this one is a little bit different than how we've done the fluid problems. Our work integral here is going to be this weight right here times our distance, which is going to be our dx. And how much do my bounds need to be? Well, how much does my x vary? Because that's the variable that we're using here. It's a 100-foot long chain, so I initially am going to start with 0 length of chain wound up, and I want to eventually end up with 100 feet of chain wound up. So x needs to range between 0 and 100. Okay, so we want to wind up that whole length of chain, so we want to go from 0 to 100. So there's our work integral. You're not going to actually have a distance function like we have in the previous problems. Your distance is going to be this dx, and this is your force. So it's your integral of force times dx. Now to actually integrate this, we're going to pull out that 1/10, and the integral of 100 is 100x. The integral of x is x squared over 2. When I plug in 100, I'm going to get 100 squared, or 10,000. And then I'm going to get 100 squared again, divided by 2. And when you punch that in, you get 500. My units here, I've got pounds and feet going on, so this is going to be 500 foot-pounds of work. Okay? So this is how I like to think of my chain problems when I'm trying to calculate the amount of work to wind a chain. Now, alternatively, doing the same exact problem, I'm going to show you how the book presents it. So what the book does is it imagines that the chain is divided up into small sections of length, which I'm going to call delta y. So this little small sort of cross section of length is my delta y. Now the distance off the ground is y. I'm going to measure this y from the ground on up. So if I need to raise up this little section of chain, how much does it need to be raised up? Well, the entire chain is 100 feet long, so if this much of it is y, then what's left here must be 100 minus y. So the distance that I need to move this section up is going to be 100 minus y. So that's our distance function, just like we had sort of a distance function in those fluid problems. Our weight is going to be the weight of this cross section, which is going to be that linear density, that 1 pound per 10 feet that we figured out earlier, since the chain was 100 pounds for, 10 pounds for 100 feet. So we're using that linear density of the chain times the little width of this chain, which is what we're calling delta y. So this is very similar to how we did those fluid problems, but we're thinking of it in terms of a linear distance. Okay, so then our work would be this weight, which is just 1/10, and that delta y becomes our dy, times our distance that it needs to travel, and that little section of chain needs to travel 100 minus y feet. And then the bounds on this, again, y needs to go from 0 length of chain all the way up to 100, so my bounds would be 0 to 100. So it's exactly the same integral that I got up here, just thinking about it in a slightly different way. And this is more consistent with how we presented the fluid problems. But again, I personally like to think of my chain problems this way because it makes more sense to me. And we'll do some more examples so that you can get some more practice. So since these two integrals are going to be the same, you're obviously going to get the same answer, 500 foot-pounds of work. Okay, so let's try another example. Using this same chain, 100 feet long, weighing 10 pounds, when is 1/2 of the work done? Well, we knew that it took 500 foot-pounds of work to do all of the chain wound up. So half of that would be 250 foot-pounds of work. So we want our work to equal 250 foot-pounds. So how much do we need to wind it up so that that much work is accomplished? Well, remember our integral for work up here, whichever way you want to think about it, was this 0 to 100, 1/10 of 100 minus x dx. So it was that linear density times the amount of chain left to wind up from 0 all the way to the end of that chain. Well, that's not going to change in this problem because the scenario is still the same. So my force, or my weight, of this chain is still going to be 1/10 of a pound per foot times that 100 minus x feet that we have left to raise up, and I'm going to integrate that weight over dx, and I want to figure out how much I need to wind up so that this work integral is equal to 250. So we know we're going to start with winding up 0. The question is, how far do I need to wind it up so that I end up with 250 foot-pounds of work accomplished? So the question is, what should I wind it up to? Let's call that L. So this one is really asking for that upper bound. How much should I wind up so that I accomplish 250 foot-pounds of work? So this time, we already know the integral, we already know what we want it to equal, we just need to figure out what that bound needs to be to make this happen. So I'm going to pull out my 1/10, and then I'm going to integrate my 100 minus x. So that's going to give me 100x minus x squared over 2 from 0 to L. So plugging in L gives me 100L minus L squared over 2. Plugging in 0 makes both of these 0. So if I multiply both sides by 10 to get this 10 out of the way, this becomes 100L minus L squared over 2 equals 2,500. Then I'm going to go ahead and multiply everything by 2 to get rid of this fraction. So then we'll get 200L minus L squared equals 5,000. And this is a quadratic equation. So if I get a 0, I'm going to have L squared minus 200L plus 5,000. And you're going to have to use quadratic formula on this because it doesn't look like it's going to factor to me. So quadratic formula would be minus the b, which makes it positive 200, plus or minus the square root of b squared, so negative 200 squared, minus 4 times a, which is 1, times c, which is 5,000, all over 2 times a, which is 1. And then you can use your calculator for that. You're going to get two solutions. One of the solutions is 170.71 and the other solution is 29.29. So which one is the answer? Well, it can't be the 170.71 because we only have 100 feet of chain. So this is too large. So that means we need to wind up 29.29 feet of chain to use 250 foot-pounds of work. Okay? All right. Next question, same chain, 100 feet long, weighing 10 pounds. Find the work done to wind the chain 3/4 of the way. So we have 100 feet of chain, we only want to wind up 3/4 of that. So 3/4 of 100 feet is going to be 75. So we want to wind up 75 feet of chain. So my work is going to be that same 1/10 times 100 minus x. This is your linear density, that amount of pounds per foot, times the number of feet that we have left to wind up, dx, and we want to do this from 0 up to 75 feet. So this becomes 1/10 times, when I integrate 100, I get 100x. Integral of x is x squared over 2, and we're just going to plug in 0 and 75. So we get 7,500 minus 75 squared over 2. The 0 gives me zeros, and this is 468.75 foot-pounds. So in all of these past few examples, we've been using the same work integral each time. We just changed the bounds on it. Okay? All right, a new situation. Find the work done to raise the chain 40 feet above ground, assuming the chain has a 500-pound weight attached. So I'm going to show you again the way that I like to think about this. We're going to assume that I've already wound up X amount of chain. So what does that mean in terms of the amount of chain left hanging down? So how much chain is still hanging down here if X of it is already wound up? Well, the whole chain was 100 feet long, so that means I have 100 minus X left hanging down. That weight is the force that I need to move through a certain distance. Now on top of that weight of that chain, we also now have this extra 500-pound weight hanging on the bottom. And that 500-pound weight is a fixed force. It's not changing over time. It's always 500 pounds. Okay? So to calculate the weight that we need to move, which is going to be our force, we have two things to consider. We have the chain, and then we have our weight, our extra little 500-pound weight hanging down. So what is the weight of just the chain? Well, remember that we had 10 pounds of chain for 100 feet of length, so that was 1/10 of a pound per foot. That's called the linear density of this chain. So if I want to calculate the weight of this chain hanging down, I take that 1/10 times the length that I have. So this is going to give me pounds per foot times feet is just pounds. So this is the weight of this chain hanging down. And then on top of that, we have an additional 500 pounds of weight hanging down, and that's not changing. That's that fixed force. So that's just going to be plus an additional 500. So my work is going to be the integral of this weight function times my distance dx. And I want my bounds here to be starting from 0, and we want to raise this chain 40 feet above the ground. So that means we need to wind up 40 feet of chain so that that weight is 40 feet up. So my bounds should be from 0 up to 40. So here's my work integral. To actually integrate it, I'm going to pull out that 1/10 from the first part. I can split this into 2 if you want. It's up to you. Think of this as the work to do just the chain plus the work to do the weight that's hanging down. So this is going to be 1/10 of 100x minus x squared over 2 plus 500x, and both of these are going from 0 to 40. So if I plug in my 40, I'm going to get 4,000 minus 40 squared over 2 plus 500 times 4 It's 20,000, and when we plug in zeros here, here, and here, all of this goes to 0. So I don't need to use that 0 bound at all. It doesn't contribute anything. And when we punch all this in, we get 20,320 foot-pounds of work. Okay, next example. This time we have a 100-foot-long chain weighing 5 pounds and has a 20-pound bucket containing 60 pounds of sand attached. Find the work done in winding the chain. So again, I'm going to assume that my X is the amount of chain that has been wound already around this pulley. So if I already have X pulled up, and this was a 100-foot-long chain, then that means the amount of chain I have left still hanging down and causing me to have a weight that's pulling me down is going to be 100 minus X. On top of that, I have a 20-pound bucket, and inside of that bucket I've got 60 pounds of sand. Okay, so those are going to be some fixed forces as well. Now, in this problem we have a new linear density because we have a 100-foot-long chain and it weighs 5 pounds. So the chain is 5 pounds per 100 feet. So this is going to be 1/20th pound per foot. So let's calculate our weight hanging down. That's going to be the weight of the chain that's hanging down. So to calculate the weight of the chain, we need to know its pound per foot, which is this 1/20th pound per foot, times the amount of length or feet that's hanging down, which was this 100 minus X. So that's the weight of the chain pulling down. In addition to that, we have the bucket, which is a constant force of 20 pounds. And then inside of that, we also have the sand, which is a constant 60 pounds. So my weight function looks like this, which means my work integral is just going to be the integral of all of this times dx. I'm going to go ahead and combine the 20 and the 60 to get 80. So here's my work integral. And we want to wind the entire chain, which was 100 feet long. So we want X to wind up from 0 up to 100 feet. So my bounds are going to be 0 to 100. So to integrate this, I'm going to take my 1/20th, and when I integrate 100, I get 100x minus x squared over 2. And the integral of 80 just becomes 80x. And I'm going to plug in my 100. So I get 10,000 minus 10,000 over 2 plus 8,000. When I plug in 0 here, here, and here, all of this goes to 0. And when I compute that, I get 8,250 foot-pounds of work. Okay. Now, a twist, same problem, but this time, what if the sand is leaking out at a rate of 1/5 pound per foot? Okay, so what that means is we're losing sand at a rate of 1 pound per 5 feet that we raise that sand up, and that's the same as raising up that chain as well, since the bucket and the sand is attached to the chain. So again, in my little diagram here, we have this chain hanging down, we've got our bucket, but there might be a hole in the bucket, so the sand is leaking out. Okay, so we're going to assume again that we have X amount of chain already wound up, which means in this 100-foot-long chain, I still have 100 minus X feet of chain hanging down. So the first thing we need to consider in terms of the weight of all this stuff is that the weight of the chain is going to be that linear density, and from the previous problem, that linear density, since it was 5 pounds per 100 feet, was 1/20th. So this is going to be 1/20th, 1 pound per 20 feet times 100 minus x feet. So this is the weight of the chain hanging down. Then on top of that, we had the weight of the bucket. And the bucket is a fixed amount here. It was just 20 pounds. And then initially inside of that bucket, we had the sand, which was initially 60 pounds, but we're losing sand now at a rate of 1 pound per 5 feet. So I'm going to take away from that 60 pounds 1 pound per 5 feet that I raise up this chain, or I wind up this chain. So this is going to be minus 1 pound per 5 feet times every x feet of chain that I wind up. So this is going to be the amount of lost sand that I'm subtracting off. So cleaned up, this looks like 1/20th 100 minus x plus 20 plus 60 is 80, and then this is going to be a 1/5 times x. You need that x in there because this is again sort of like a linear density in terms of the amount of sand that we lose, so it's dependent on how high we raise it up, which corresponds to how much chain we wind, which is what we're calling our x. So this is now our new weight function. So the work integral is going to be the integral of all of this stuff times dx. There's our weight times our distance. And our bounds here, we want to wind up this entire chain, so we're going all the way from 0 to 100. So the integral here would be 1/20th times 100x minus x squared over 2 plus 80x minus 1/5 times x squared over 2. So you can change this denominator, if you will, to just a 10. And then my bounds are 0 to 100. So you plug those in. And this gives you 7,250 foot-pounds of work, which is less work than what we had before. And that should make sense because we're losing sand. So the amount of weight hanging down gets less and less as we raise this up. So we have less weight, which means it requires less work to move it up. So that's why our final answer should be less than what we got earlier on. Okay? Last two examples. What if the chain weighs 1/2 of a pound per foot? So this is our new linear density. They're already telling me that fraction to use. So for our chain, it weighs 1 pound for every 2 feet. And we have 40 pounds of sand have leaked out when the chain is fully wound. So this time, instead of telling me, like in the last example, that the sand is leaking out at a rate of 1/5 of a pound per foot, where they actually gave me that rate already, in this next example, they're not giving me that rate right away, but they're giving me enough information to figure it out. So the lost sand, we lose 40 pounds of sand have leaked out when the chain is fully wound. So if 40 pounds have been lost for the full length of the chain, which was 100 feet long, then this reduces to the fraction 2/5. So 2 pounds of sand lost for every 5 feet of chain that is wound up. Okay, so these are going to be our new linear densities. This is the linear density for the chain. This is that linear density for the sand. And this sand one we're actually going to subtract off because we're losing the sand, so we want to subtract off the weight, which makes it lighter, which makes the work less. So our weight is going to consist of, remember our pulley situation here again, we've got X amount of chain wound up which means we've got 100 minus x left to wind up in length. So the chain hanging down is going to be 1 pound for every 2 feet. That was that linear density they told us in the problem, times 100 minus x feet that's hanging down. So the weight of this chain is 1/2 of 100 minus x. That's just from the chain. Then we have the bucket, which is a constant 20 pounds. Then we have the sand, which initially is 60 pounds, but we're losing sand at 2 pounds per 5 feet. So we want to subtract off from this 2 pounds per 5 feet times the number of feet that this is moving up, and that's the amount that we've wound up already, which is what we're calling our x. So this is going to be 60 minus 2/5 times x. So this part right here is the lost sand. So my weight function is going to look like 1/2 100 minus x plus 80 minus 2/5 x. So in these chain problems, once you figure out that weight function, then your work integral is just the integral of that weight times your dx. So all of this weight times dx, there's my force times my distance, and my bounds here, I want to wind up this chain, I want it fully wound, so I want to go from 0 all the way to 100. So there's my work integral. To integrate it, I'd get 1/2 100x minus x squared over 2 plus 80x minus 2/5 x squared over 2. So these 2's are going to cancel, and my bounds are 0 to 100. So I'll leave that for you to plug in. Only the 100 will impact the answer. The 0 will go to 0, and this gives you 8,500 foot-pounds of work. Okay? All right, last one here. What if the chain weighs 8 pounds and 10 pounds of sand are left when the chain is fully wound? So the only thing that's changing in this last problem are going to be those linear densities. So this time for the chain, it weighs 8 pounds for this 100 feet of length that we had. So that new fraction for the chain is going to be 2/25 pound per foot. And for the sand, this time the lost sand, we have 10 pounds left after fully winding the chain 100 feet. So if 10 pounds are left, how much was actually lost? Well, remember we started with 60 pounds of sand. So if I am left with 10 at the end, I must have lost 50. So 50 pounds of lost sand for 100 feet of wound up chain. So this gives me a fraction of 1/2 pounds of lost sand per foot of chain wound up. So my weight is going to consist of that chain hanging down, which is in length 100 minus x if I already have x of it wound up, and that length of chain, that 100 minus x, is 2 pounds per 25 feet. So this gives me the total number of pounds of that chain hanging down. So that's the weight of the chain. Plus, we have our bucket, and our bucket was 20 pounds. Plus, we have our sand, which initially was 60 pounds, and then we're losing 1 pound per 2 feet. So 1 pound divided by 2 times the number of feet that the chain got wound up, which is what we're calling our x. So this is going to be our lost sand, that minus 1/2 x. So this weight, simplified, is 2/25 times 100 minus x plus 80 minus 1/2 x. So our work integral is going to be just the integral of all of this weight And we want to do this for the entire length of the chain, so my bounds are 0 to 100. So to actually integrate this, we're going to get 2/25 times 100x minus x squared over 2 plus 80x minus x squared over 4, because we get a 2 in the bottom times that other 2 we already had there, from 0 to 100. And if we plug in our bounds, we're going to get all of this stuff, and you can use your calculator to realize that all of this comes out to 5,900 foot-pounds of work. Okay? So we talked about three main types of work problems. The work required to stretch or compress a spring, and that relies on that force function F equals kx, which is Hooke's law. Then we talked about the force required to move a fluid, which requires you to take a cross-sectional slice, find the weight of that slice, and multiply that by the distance that that slice needs to move. And then finally we talked about the work it takes to wind up a chain or a cable, and to figure those out, we figure out the weight of the cable or the chain that's hanging down, plus any other additional weights that are hanging down from that chain, and then you integrate that weight over your bounds. Okay? These take some practice, so just work hard at it. Good luck.